Hi everyone, I'm Gon from KAIST in South Korea. I'm presenting our work about how do hyperedges overlap in real-world hypergraphs. In this work, we examine patterns, define measures, and develop a new hypergraph generators. What is a hypergraph? Hypergraphs consist of a set of nodes and a set of hyperedges. They can be found in many different areas, including collaborations of researchers, co-purchases of items, and joint interactions of proteins. Each hyperedge is a subset of any number of nodes, and due to its size flexibility, hyperedges can overlap in infinitely different ways. In this work, we propose tools for answering three interesting questions. First, how do hyperedges overlap in real-world hypergraphs? Hyperedges can overlap in infinitely different ways, so it is much more complicated and difficult to analyze such patterns than in graphs. Are there any non-trivial patterns that distinguish real-world hypergraphs from random hypergraphs? We compared the overlapping patterns of hyperedges in real-world hypergraphs to those in random hypergraphs. How can we reproduce the patterns through simple mechanisms? We propose a novel hypergraph generation model that creates a realistic hypergraphs that preserve the patterns observed in real-world hypergraphs. Before sharing our observations, we introduced our null model. We propose HyperCL, which is based on the Chenglu model in graph generation. Given the distributions of hyperedge sizes and node degree distributions, for each hyperedge, we sample the nodes with probability proportional to the degree of each node. Hypergraphs generated by HyperCL empirically preserve the input degree distribution of the input hypergraphs. Throughout this work, we use 13 real-world hypergraphs from 6 different domains. We examine overlapping patterns of hyperedges in real-world hypergraphs and verify them by comparing with those in random hypergraphs obtained by HyperCL. We investigate the overlaps of hyperedges at 3 different levels, and first, let's take a look at Egonet level. Here, our question is, how substantially do the hyperedges around the node overlap with each other in the real-world hypergraphs? To answer to this question, we measure the density and overlapness of the egonets in the hypergraphs. An egonet of a node in the hypergraph is defined as a set of hyperedges that contains the node. The density of a set of hyperedges is defined as the number of hyperedges divided by the number of nodes. So intuitively, more hyperedges overlapping in a fixed number of nodes makes the sub-hypergraph have higher density. We measure the densities of the egonets in real-world hypergraphs and those in randomized hypergraphs, and observed that egonets in real-world hypergraphs tend to have higher density than those in random ones. However, does density fully capture the degree of overlaps of a set of hyperedges? Consider following two sets of hyperedges. Intuitively, the left one is overlapped more substantially than the right one. But the densities of both sets are the same since they have the same number of nodes and the same number of hyperedges. Then, what is the principled measure for evaluating the degree of overlaps of a set of hyperedges? To address this issue, we present 3 axioms that any reasonable measures of the hyperedge overlaps should satisfy. First, given the same sized hyperedges and same number of nodes, one with more hyperedges overlaps more. Second, given sets of the same number of hyperedges and the same hyperedge size distributions, the one with less distinct nodes overlaps more. Finally, Given sets of the same number of nodes and same number of hyperedges, the one with larger hyperedges overlaps more. Based on the three actions, we define a new measure called overlapness of a set of hyperedges. Instead of taking the number of hyperedges into consideration, we divide the sum of the hyperedge sizes by the number of nodes. Then, we measure the overlapness of the egonets in the real-world hypergraphs and those in random hypergraphs. Our observations show that the egonets in real-world hypergraphs tend to have higher overlapness than those in randomized ones. The proposed measure, overlapness, satisfies all the actions while others do not, including density. Now let's move on to our second level of observation. Here we try to answer to the question how many hyperedges overlap at a pair or triple of nodes in the real-world hypergraphs. While the degree of a node in a hypergraph is defined as the number of hyperedges that overlaps the node, we extend the concept to pair and triples of the nodes. So we measured the distributions of the number of hyperedges overlapping at each pair or triple of nodes. Compared to the random hypergraphs, the distributions in real-world hypergraphs is more skewed with a heavier tail. Furthermore, we observed that the distribution follows the power law distribution. Now let's move on to our final observation. Our question is, how structurally similar are nodes that form hyperedges together related to each other in the real-world hypergraphs? In order to answer to this question, we define a new measure to investigate the similarity. We define homogeneity of a hyperedge, which is the average number of hyperedges overlapping at all the pairs of the nodes in the hyperedge. Compared to the hyperedges in the random hypergraph, those in real-world hypergraphs tend to have higher homogeneity. Now let's move on to our algorithm HyperLap and HyperLap Plus, which generates realistic hypergraphs. We first introduced our base algorithm HyperLap. The main idea is extending the HyperCL to multiple levels. Instead of generating hyperedges from the entire set of nodes, we first partition the nodes into groups at every level. Specifically, at each level, it randomly divides nodes into equal-sized groups, and the groups are hierarchically designed. So, if nodes are in the same group at some level, then they are in the same group at all lower levels. Given the weights of each level, we first select a level with probability proportional to each level. Then we select a group in the level uniformly at random. Once the group is selected, we generate a hyperedge by sampling the nodes with probability proportional to its degree. So, to sum up, instead of taking all nodes into consideration, we divide the nodes into multiple groups and limit the nodes that a hyperedge can contain into those in the group. We also design an advanced version of HyperLap called HyperLap Plus. This model automatically tunes the parameters of HyperLap, so it automatically searches for the weights of each level. As its objective function, HyperLap Plus uses the hyperedge homogeneity distance, or HHD, between the input hypergraph and a generated hypergraph. We used these statistics between the cumulative hyperedge homogeneity distributions of the two hypergraphs. At first, we generate all the hyperedges at level 1, so it is equivalent with HyperCL, which generates hyperedges from the entire set of nodes. Then we replace some of the hyperedges at level 1 to level 2. The ratio of the replacement is searched by our objective function HHD. In the same way, some of the hyperedges at level 2 is replaced to level 3. This is repeated until convergence, so it continues until the HHD does not decrease anymore. HyperLap Plus reproduces most accurately the distributions of Egonet density, Egonet overlapness, and hyperedge homogeneity distributions. In other words, these statistics between the distributions of real-world hypergraphs and those in the generated hypergraphs is the lowest in HyperLap Plus. HyperLap Plus reproduces the heavy-tailed distributions of the number of overlapping hyperedges at each pair and each triple of nodes accurately. These statistics between the distributions of real-world and random hypergraphs is the lowest in HyperLap Plus. The proposed methods, HyperLap and HyperLap Plus, scale near linearly with the size of the input hypergraph. Let's wrap up the presentation. We first investigated the patterns in real-world hypergraphs in 3 different levels. Then we proposed new measures, overlapness and hyperedge homogeneity. Finally, we designed a novel hypergraph generation models, HyperLap and HyperLap Plus. This is the end of our presentation. Thank you for your attention.